Hello viewers, it is Abdurrahim Babatunde again for this channel, New Episode Design. How are you guys doing? Hope you are enjoying our video. Actually, I saw some of your comments and feedback on my last video on advanced petroleum refining in Aspen HYSYS. So I'm really glad to actually see your feedback and to see your comment on my work. I'm actually glad that someone is actually seeing my work and it is helping them to learn more about Aspen HYSYS. For the new viewers, this channel is for chemical process design. So on this channel we upload video and share content on chemical process design software, and it is brought to you by Nubra Process Designer. We are a process design consultant firm. We help students and professionals on their project, research project, or anything that you want to work on. We can help you on your projects and get it done. And if there is any problem, like any discussion, like you can always drop the comments on the comment section or message us through our contacts. We'll be happy to help you on your project. So on this note, I would like to continue from where we stopped in the previous video, because I said in the previous video, which is Aspen HYSYS, like advanced petroleum refining with Aspen HYSYS, I mentioned that we are going to be continue vacuum distillation column in another video, which is this. So from the vacuum distillation column, we have the HVGO, the diesel, the naphtha, the atmospheric residue. So the atmospheric residue is like the heavy crude that is taken at the bottom of the atmospheric distillation column. So the crude is actually mixed with a vacuum coil stream before it is created in the vacuum heater, where it is heated to the temperature of the entry temperature of the vacuum column. And from the vacuum heater, there will be a period drop. When I'm doing the simulation, you understand better. There will be a period drop because the minute vacuum column is or column that is operated at a very low pressure. So it's going to reduce the pressure to that low pressure that we are going to be using for the vacuum or operation pressure for the vacuum column. And there is a vacuum stream to steam strip the vacuum column. And because the column configuration, for the column configuration, I'm going to go to the column environment for you to show the column configuration better. So for the column configuration, is the vacuum column is like an absorber, like the unit operation that we are using Aspen HYSYS is an absorber. So but the liquid feed from the top is going to be from a pump around that is taken from, like we call it LVGO pump around, that takes its flow from stage 2. You can see its flow is taken from stage 2, its draw is taken from stage 2, then it's pumped out to the top stage, you understand. So this will serve as a condenser for us, but it's a pump around, you understand. So this is like a complex, a special kind of column. So then we have another pump around, which is the HVGO, that is every vacuum gas oil pump around. Then that one is taken from stage 8 and is pumped back to stage 5. And we have three liquid draw. We have the low vacuum gas oil draw, the heavy vacuum gas oil, and the slope wax draw. Then from there we have the vacuum residue, which can be processed in further units. So the meaning of using this vacuum column is to get more products from our crude oil before because this vacuum count residue is mostly used for asphalt blowing, like heavy products, petroleum products. You understand that nothing in petroleum, no component of petroleum crude oil is not useful. They take a lot of products from crude oil, you understand. So that's all the thing. So this vacuum cooled residue can still be processed further, and we have the feed coming at stage 12 and the vacuum column steam at the bottom, which is stage 14. The number of stages in the vacuum column is 14 stage. So I'll go back to the column menu here. So from there we have I'm going to be doing most of the configuration. So this is just what I've done so that to make the video shorter and not to waste more time setting up the video. So you can do this on your own, just set it up and connect the stream and everything. Then we have these are the duty stream. You understand, you can put the duty stream if you like, you can remove it if you don't like that sort of thing. So we have so I'm going to be starting here today. So we are using this textbook to get the operation parameter again, so that we are getting some reasonable estimate for the result first before we start to improve on it. So we have the so I'm going to be starting with the vacuum coil stream. I'm putting the input and the composition. So watch out. So we have the vacuum coil stream. So let me get to the vacuum coil stream. So the vacuum coil stream is having like typical temperature and pressure for the other steam. So 500, I think all the stream is taken from the same source, all the steams. So 500 Fahrenheit, and the temperature is 150 psig. So we have the flow is, let's do the composition, which is same thing as just having water. That will be the composition for the steam. Then I will normalize it, and okay, so the flow is in pounds per hour. So it's going to be 20,000 pounds per hour. We're going to pounds per hour here. So the steam has been fixed. So from there it has flashed the mixer instant and the period of the mixer and everything. So I'll do the flash calculation for the heater. So for the heater, I'm going to be checking this because the heater, you can see from all these data for the vacuum column, we have number of stage, 14 stage, like for explaining the efficiency. We are going to be doing that later using the method of group efficiency. Then the condenser, there's no condenser, and so a pump around is used to return the stream to the top stream, the liquid stream to the top stream. So direct heater, fire heater, for instance. So this is the period, very low period, 50 mm mercury and 62 mm mercury. This is the top stage temperature. So this temperature has to be controlled based on what they are saying there. They are saying the top temperature is 180 Fahrenheit and is controlled by this flow, by this pump around temperature and stream temperature and flow. So if the temperature is high, so it's going to cool down the stream lower, you understand, so that the temperature will reduce for that stage, so that we are getting a reasonable product. So we have the crude oil to be coming to tray 4, and we have the crude oil to be coming to tray 12, and the stepping stream at the bottom, tray 14. And at this rate, so I'm going to be I'll do this one later. So I'm going to be doing the feed heater. Feed heater is okay. Okay, injected stream. Okay, this is the coil stream that I just did. Injected stream, and is having temperature of 500 Fahrenheit and 150 psig, and it is injected with the atmospheric residue. You understand? So the outlet of this feed heater is 180 mmHg and 760 Fahrenheit. You understand? So I'm going to be doing this 180 pressure. That will be the flashing pressure and the flashing temperature of the heater. You understand? So you to calculate the duty that is required for the heater. So I'm going to be doing 180 mmHg. So you choose mmHg to be not this gram scale, just the normal one. mmHg as 0 degree Celsius. So we have the temperature to be 760, so high temperature. So 760. The main reason of reducing the temperature because to reduce the equilibrium temperature. That's the main reason of reducing the pressure. So if you reduce the pressure for the saturated temperature of the residue will reduce. You understand? So you can reduce you will not be using higher energy in order to fractionate the residue to remove quality product like vacuum gas oil from the residue, atmospheric residue. So you can see the quality or vapor fraction is 0. The quality should be 1 minus this is 0.8102. So that's the vapor fraction. That is some component has already flashed out of the residue stream. So that's also so we have the vacuum column steam. So I'm going to be doing vacuum column steam next, based on the data that I have here. Where's the okay? This is the steam. So we have the steam here. Oopsie, feed. Okay, steeping stream. Yeah, 500 Fahrenheit and 150 psig. Basically like the same thing. 150 psig, then 20,000 here. Okay, I got it. 20,000 pounds per hour. Should just compare with the others so that 9.2. So I'm going to be doing the composition to be 1.2. Okay, normalize. So I've done this. So let me check. I've just checked this once. Okay. Let me check the composition. You can check the composition here again. You can even do it there. There are a lot of ways of doing things in Aspen HYSYS. So the next thing is to do the prayer. So to do the prayer, though, we have a PSIG prayer here. I think it has flashed the prayer based on the stream, I guess. So I'm going to do another prayer configuration based on the data that I have here in order to get a reasonable result for my simulation. So okay, so where's the prayer? 50 psig on the top, 62 at the bottom. So before I do that, I'm going to go to this and remove. Okay, there's no data for it. Okay, I'll just do it here. So let me just do 50 mmHg and 62 mmHg. Okay, so check again. 62 mmHg. So the pressure has been configured. So it has interpolates the pressure network so that the pressure drop is proportionated. So we have the the next thing I'll do is the efficiency so that to make this thing faster. So I'm going to be using group efficiency, and I'm going to define the group here. So to define the efficiency, just I want to, like I did in the previous video, I want to reduce the timing. You understand? So I'm going to be making this stage 2 to be stage or group 0. then this will be group 1, so this will be group, okay, this will be group 2, okay. So it's going to be 3 groups. So okay, so for group 1 we have J1 and 12, J1 and 12, J1 and 12, and this one will be J2, and this will be J2 too. So I'm going to be making this one to be 0.5. Group 1 will be 1 because it is 100%, and group 13 to group 3, no, group 2, which is trade 13 to trade 14, will be 30%, which is 0.3. So because the efficiency is fractional over here, not in percentage, so it has input the efficiency there in the for the each stage. So from there, I'm going to, let me check any data that I can add. So it's not much data, so I'm going to be adding spec currently and inputting all this data to the spec configuration that is already, because there are some default spec that will come, so every time you create a column, you understand. So I'm going to be putting the data that is for the spec in the monitor page here. So we have the monitor here, so I'll add first, because something is very important in this simulation of this vacuum column, which is the temperature, because the flash like the composition of the vapor and the liquid equilibrium, that is stage composition, depend on the vapor liquid equilibrium of the that is the component of the mixture, which is all these petroleum components, all these higher boiling point component, and the light boiling point component. So it depends on the temperature and the period. So you have to get the temperature right if you want to get the composition right. You understand? The flash we only converge when the composition has converged and the flow has converged. You understand? So I'm going to be making a temperature spec of 180, trying to get everything to get this temperature of the top stage to be 180. You understand? So once the temperature of the column, of the top stage of the column is 180, then I'm closer to solution of the column. You understand? So I'm going to be doing temperature spec first. So column temperature. So I'm going to be adding top stage temperature, that is 1 made over, then I'm going to write 180 Fahrenheit. So oops, oh, let me change this name to top 3. Top temperature, so that I'll be able to distinguish it. So I'm going to be adding another spec. Let me check any spec. Okay, we can add the product specification, that is the distillation specification for the products. So we are going to be adding D11 distillation 1160, that's this 95% cut point. I think it's going to be by volume. You understand? So this is the flow specification for the light vacuum gas oil. So I'm going to be adding the cut point temperature for the flow. You can see this spec here. We are going to put this spec here. So I'm going to be using cut point as I did in the atmospheric column. So it is in stage 4, because you cannot specify for the stream for this cut point for stream, so you have to do for stage. So the logic is like any flow, any stream that is coming out of any stage, you have the same composition, this the same properties of the stream in that stage. So that is why. So we have the D160 atm atmospheric, then volume fraction. So I'm going to specify 95%, and the temperature to be 915. This is much higher temperature because we are now in vacuum, we are distilling residue. So we have 95 cut points, 915 Fahrenheit, volume fraction. Okay, so let me change the name to, so that I can distinguish it from heavy vacuum gas oil. So we have the LVGO cut point. So I'm going to be adding for the heavy vacuum gas oil. So the stage for the heavy vacuum gas oil is stage 8. Okay, stage 8. Then I'll change the type to be D1160 ATM. So liquid to 95 because the draw is also in liquid state, not in vapor. So we have 1050 Fahrenheit. 1050 Fahrenheit. So let's change the name to LVGO, HVGO cut point. Oh, sometimes you have to be very careful in running all these things. It's because the spec is not available. That's why it's not running yet. It's automatic. So the next step for me is to put all this spec based on the data that I have here. So I'm going to start with the pump params. So for the pump params, we have the flow to between 20,300 for the top, the LVGO pump param. So this is it here. Top stage. That's why they give it top stage. Just so that top stage pump param. So I'm going to standardly follow. So 22,300. So for this duty, this is data T. So I'm going to put the value there, although I might change the value later. So it's going to be a return temperature. So the return temperature that they put as estimate here is 85 degree Fahrenheit, although it can change later because our main focus is on getting the top state temperature to be 180. So it's 5 Fahrenheit. So have changed the return temperature. So the duty, they give us the duty to sometimes the temperature might not be accurate spec, so we'll just be playing around the duty, the specification. So the duty is minus 40 because it's cooling, so it's going to be minus 42 mmbtu per hour. So I'm going to specify minus 42 mmbtu per hour, something at the bottom here. So okay, so this is the second pump around rate. So I'm going to be specifying the second pump around 8 rate to be 50,000 barrel per day. 50,000 barrel per day. Oops, this is also in more weight, so I have to change it to kilo volumetric rate. But the first one is not in more weight, as some are fun. So this is 50,000 barrel per day E4. Okay, so this will be temperature. I think they gave us the temperature difference. Okay, they said 150 degree cooling, so it's supposed to be temperature different, you understand? So that's the meaning, 150 degree cooling. So it's going to cool it no matter, like, in as much any temperature that is coming, it's the stage the draw is coming from, it's going to cool it to minus 150 degree Fahrenheit. So I'm going to specify 150 here. So, and you can see temperature drop over here. Is it in degree? It's in 150 Fahrenheit, not degree. So I'm going to say 150 Fahrenheit, 83.3 degrees C. Okay, my temperature drop in unit is in degrees C. So that's why you are saying degrees C. So we have the LVGO rates. For the LVGO rates, we have 5,000 barrel per day. So I'm expecting to get 5,000. This is also in volumetric. Let me do doing over here. Is in molar flow, I mean. So 5,000 barrel per day. So the HVGO rate is 21,000 barrel per day. It will be in molar flow. Let me use the 21,000 barrel per day. What's the slope wax? 1000 BP barrel per day. So 1000. Okay. Change it back to standard volumetric flow. Okay, so we have this. So I'll try to specify the pump around rate, and this is the process itself, not really the product purity or something. And this temperature is very important, like I said. So I'll try and get to this temperature. So I'm specifying the product rate now so that you calculate the material balance. Because if you are saying the inlet flow, before you can specify the outlet flow, you must make sure that your material your product flow is up to that. So if you check the product flow liquid volume barrel per day, you can see this is a very high flow in. So if I'm specifying 21,000, I'll be able to get it. You understand? And I try to make sure that my residue is basically what they got in the textbook. You understand? That's why I'm specifying. I'm using these products here. I'm using all these product specification here. All these product specification here, product rate, so that when when the material has been summed up, I will be able to get a residue that will be up to the task in the LVGO. So the residue flow that will be up to the task in the LVGO. So we have the residue. This is the flow of the residue barrel per day, 4.76796 times 10 to the power 4 barrel per day. You understand? So that's that. So I'm going to be specifying, just remain to specification. So let me just pick this and this and see how it's solved. You can check the convergence here in the equilibrium and its spec. Once is very low, that's and is below the tolerance, that's when to converge, and voila, it has converged. So we have the 85, we have this flow, and we have the inlet temperature here. So that's that. So this is the pump around rate, and the temperature and everything. And although this cut point that I'm getting is very low, the distillation cut point, so the product is not, I have to adjust the operation and my crude. I can do that one by adjusting the crude specification here. So to do that, I'm going to be changing this, but before I change, I will delete first. So let me delete. So I'm trying to change this one to be very low, every crude 0.01. Let me delete the second one first too, so that I just do it once. 0.01, and this will be 0.9. I want to increase the value of the light crude a lot, so it has calculated everything. So I'm going to check. Let me check this one first. You see that the stream will get closer to the spec, because I think the crude that they are using in this simulation is mostly light crude, like contain light components, and so you can see this is much closer to the naphtha cut or specification that we have here, and kero cut and everything is closer now, and 750. And the temperature has not reached 250 yet, but temperature is not the big thing in the atmospheric distillation column. So let me check the vacuum column and see how it influences the kind of how you blend your crude, how it influences your operation and your resources. So for this we have 8. This has increased, you understand, and it is now much closer to the value, and we are now getting a better result. And this has moved closer to 1050 for the cut point for the heavy vacuum gas oil, and that's very good. So, and you can do any kind of analysis from here. And for the column, we can get can go to column environment to see some of the information about the column. You can see the column environment has converged to, it's running the same way. So you can see the duty here, So this is the duty that is for the heavy vacuum gas oil duty, and this one has already been seen in the monitor tab. This is the duty value. Is a bit although I specifying in MMBTU per hour, so it's not the same thing. So we have the flow. The flow here is there's a flow here in kilomole and everything. You can check everything and the composition and everything about the point, the top proper and about the column, the performance of the column, the table. This is the table for the column, the flow in, flow out. This is type draw, production, pressure drop, and feed pressure. Yes, so this is the product pressure. It's going to be using this pressure for that will be the pressure of the stage. That's what is going to be used for the draw stream that's coming taken out of the stage. Yes, so we have the temperature of this of each stage from 180 that I specified. This is the bottom temperature that we are getting. You understand? So we have the flows and can do the standard the volume load like barrel per day flow and everything some way. Although hydraulic is when you are designing or something, we are designing dynamic system or column tray hydraulic system. So I think that's everything that I want to show on, unless you want to plot some performance curve and some performance plots of the column like I did for the atmospheric column. So that's the how to do a vacuum distillation column. You just put the vacuum pressure in the column and it's more like atmospheric distillation column too, and it is solve for the column. So because our HYSYS unit operation are very versatile and really efficient. So thank you for watching this video. So on the next video we are going to do about the debutanizer. So watch out. Thank you.